All right, today we're going to talk about something really cool, an AI that's basically teaching itself the laws of physics. And the result? It's slashing simulation times. I'm talking about stuff that used to take months or even years, now taking just a few seconds. So how in the world does that work? Let's dive in.
So picture this. You're an engineer, and you're designing something incredible, like a hypersonic jet or a super tiny medical device. How do you actually test it? I mean, you can't just, build a hypersonic jet in your garage and hope for the best, right?
The answer, of course, is simulation. You use these monster computers to model all the physics. You know how air flows over a wing, or how gas squeezes through a tiny channel. These simulations are the absolute foundation of modern engineering. They let you test thousands of ideas without ever building a thing.
But, and this is a big but, here's the problem. For some of the most important cutting-edge stuff, our best, most accurate simulations are just painfully slow. And I mean prohibitively slow. This isn't just a delay, it's a roadblock. It can bring innovation to a grinding halt.
So, to really get how scientists are smashing through this barrier, we're going to zoom way in on a classic problem from fluid dynamics that is way trickier than it looks.
Okay, this little thing is called the micro backward-facing step. It's basically just a tiny channel that suddenly gets wider. Looks simple, right? Well, this shape is a standard test, a benchmark that scientists use to understand a really specific kind of flow. And the part we care about, the really interesting bit, is that little swirl, that vortex that forms right after the step.
Now, the gas flowing through here isn't like the normal air we're breathing. It's what's called a rarefied gas. Think about what it's like way up in the upper atmosphere, or inside a vacuum chamber. The molecules are so far apart they barely ever run into each other. And because of that, they stop behaving like a normal fluid. All the usual rules of aerodynamics just go out the window.
Scientists have a way to measure this thinness. They use a little something called the Knudsen number, or Kn for short. This number is everything here. If the Knudsen number is low, the gas is pretty dense. But if it's high, that means the gas is super thin. It's rarefied. And this one number completely changes the physics of what's happening.
And that brings us right back to the main problem. Trying to accurately simulate how this gas behaves, especially as you change that Knudsen number, is just incredibly hard and takes a ton of time.
Just look at the difference here. On the left, with the low Knudsen number, you see that big, obvious vortex, that whole area of backward-moving flow. But check out the right side. At a high Knudsen number, the gas is so thin that the vortex is just vanished. It's gone. Being able to capture that transition is the really tough part.
You know, the gold standard for simulating this stuff is a method called Direct Simulation Monte Carlo, or DSMC for short. It's super accurate. I mean, it tracks individual molecules, which is wild. But there's a huge catch. The paper itself calls it prohibitively expensive. And they're not kidding. A single run can take forever, which makes it totally useless when you need to test a bunch of designs quickly.
So, if the old way is just too slow, what's the new way? Well, let's introduce the hero of this story. An AI that's built not just to find an answer, but to actually learn the underlying physics itself.
Now, this is not your everyday neural network. It's called a deep operator network, or DeepONet. And here's the key difference. A regular AI might learn to predict the flow for, say, one specific Knudsen number. But a DeepONet learns the entire rulebook. It learns the mathematical operator that connects any Knudsen number you give it to the complete flow pattern. It's not just learning the answer, it's learning the relationship.
Okay, but how do you get an AI to really nail the hardest, most important part of the physics? You give it a secret weapon. And in this case, it's a really clever new way of training it called a zonal loss function.
So here's the secret sauce. Instead of the AI treating every mistake it makes equally, this method basically tells it to obsess over mistakes made inside that vortex. It's kind of like a teacher telling you, look, I don't care as much about the easy questions, but the questions about this one tricky topic, they're worth 90% of your grade. So what does the AI do? First, it finds that critical region where the flow is actually moving backward. Then, it isolates only the prediction errors inside that little bubble. And finally, it cranks up the penalty for those specific errors, like way up. It forces the AI to master the hardest part of the problem.
And this picture shows you exactly why that simple rule, just look for backward flow, is so genius. On the left, an older method highlights this huge fuzzy area. But look at the right. The new method perfectly zeroes in on the actual vortex, that green region. It gives the AI a crystal clear target to focus on. It's so precise.
Okay, so the theory is super smart. But, does it actually work in practice?
Let's check out the results and see how this new AI compares to the gold standard simulations it's trying to beat. So here we're looking at a low Knudsen number, where we expect to see a nice big vortex. On the left, that's the ground truth from the slow as molasses DSMC simulation. On the right, that's the AI's prediction. I mean, come on, they're practically identical. The AI totally nailed the size, the shape, everything about that vortex.
Now let's jump to the other extreme, a high Knudsen number where the vortex is supposed to be gone. And, yep, look at that. The AI's prediction on the right is a perfect mirror of the ground truth on the left. It correctly figured out that the physics here means no more recirculation. It didn't just memorize a picture, it learned the actual physical change.
And if you want the hard numbers, here they are. This graph is plotting the length of the vortex against different Knudsen numbers. That solid line, that's the real answer from all those expensive, slow simulations. And the dots? The dots are the AI's instant predictions, even for values it never saw during training. I mean, look how perfectly they land right on the line. It's not just close, it's quantitatively exact. It's amazing.
So what's the big takeaway from all this? Well, it means we've got a new tool that isn't just ridiculously fast, it's also incredibly accurate. We're talking about accelerating the entire process of how we discover new science and engineer new technology.
So let's just recap why this is such a huge deal. First, speed. We're going from months to seconds. It's a total game changer. Second, accuracy. We just saw it. It's not some cheap knockoff. It reproduces the gold standard results beautifully. And third, efficiency. This zonal training method is so good that the AI gets to over 90% accuracy with less than half the training data you'd normally need. Think of all the time and money that saves.
And this all ties right back to where we began. By completely demolishing that simulation bottleneck, this kind of physics-smart AI lets engineers test and perfect designs for everything from tiny new sensors to next-gen spacecraft, and do it at a speed that was unimaginable just a few years ago.
You know, what we've really seen here is a glimpse of a future where AI isn't just a black box that spits out answers, but a genuine partner in science. And it leaves you with a really big question. What's the next huge scientific challenge we can solve now that we can teach an AI not just to learn, but to focus on what truly matters?